Hi all, today in this video we are going to start the classes of functional analysis for the third semester MSc for Calicut University. So from the 2019 batch onwards the textbook have been changed. I am Dr. Sister Smitha Rose C G. So the new textbook, I'm going to deal linear spaces on this video, and the new textbook is authored by Yuli Edelman, Vitaly Milman and Antonis Solomitis, and the name of the book is Functional Analysis and Introduction. So we are following that new text in these classes for this third semester. So coming to the outline of this presentation, in this video, first we will have an introduction to linear space. Then we will deal with infinite dimensional and finite dimensional examples for linear spaces. Then we will discuss linear maps and isomorphisms in a condensed way. Then linearly independent set of vectors, dimensions, etc. So what is a linear space? A linear space or a vector space consists of the following. Four things are there. First of all, we should have a set V of objects called vectors. It can be n tuples, functions, matrices, or anything. Any set V of objects called vectors. Secondly, we should have a field F of scalars. So here in this textbook, when we are saying about a field of scalars, we are considering only this field of the real numbers script R and field of complex numbers script C. The third thing is a rule of vector addition. So as we have already studied in first semester linear algebra paper, the vector addition along with the set V along with vector addition should be an abelian group. So all the conditions of a group and especially an abelian group should be there. That means vector addition should be closed in V and associativity should be there. There should be an additional identity of addition for V. Then inverse should be there. Then since it is an abelian group, vector addition should be commutative. So thus the third thing for a linear space is a rule of vector addition, and the set V along with vector addition should be an abelian group. Then the fourth thing, a rule called the scalar multiplication, which associates with each scalar C in F a vector alpha in V. We get a vector C alpha in V called the product of C and alpha in such a way that 1 alpha is alpha for every alpha element of V. C1 C2 alpha is equal to C1 of C2 alpha. C1 of alpha plus beta equal to C1 of alpha plus C2 of beta. C1 plus C2 of alpha equal to C1 alpha plus C2 alpha. Here these four conditions are the distributive and associative conditions for the scalar multiplication operation. Now we are going to define subspaces. A subset E1 of the linear space E is called a subspace of E if it is closed relative to the linear operations in E. So there are two linear operations in E, that is vector addition and scalar multiplication. So if the subset E1 is closed with respect to those two operations, we will say that E1 subset of E. Here we are denoting this symbol for this in this textbook. Now we move on to some examples of linear spaces. First, we will consider examples of finite dimensional linear spaces. So Rn, the Euclidean space, is a linear space with dimension n Then Cn, the n-dimensional space of complex numbers. The dimension will be n if it is over C, and as we know, if the space is over R, then the dimension will be 2n, dimension of Cn, C power n. Now the fourth example is the set of all m by n matrices over F with the dimension mn. Then set of all square matrices of order n, then the dimension will be n square. Then the space of polynomials of degree less than n over a field F, then the dimension will be n plus 1. We have more examples. I was just listing some of them. Now, what is a infinite dimensional space? A linear space is said to be infinite dimensional if it contains an infinite number of linearly independent vectors in its basis. In this class, we will just see what is linearly independent, dependent and all. So, we are moving on to some examples of infinite dimensional vector spaces or infinite linear spaces. Especially in functional analysis, we will be dealing more with infinite spaces rather than finite spaces. So here, consider S star, the set of sequences with finite support. With finite support means the sequences with all but finite zero elements. In other words, we can consider an infinite tuple of AIs, and it is this tuple will be in S star if and only if there exists some n element of script n natural numbers, so that ai equal to 0 for every I strictly greater than n. So after the stage small n, all the ai's should be 0. That means the tail should be 0 in an infinite tuple. The tail should be 0. So we will denote that set of sequences with finite support by S star. This set forms a linear space with respect to the addition of sequences and multiplication with real or complex numbers, and the space can be considered as isomorphic to the space of all polynomials. Now another example that I want to give is the set C naught of sequences tending to 0, then the set C of all convergent sequences, the set L infinity of all bounded sequences, the set S of all sequences. Then maybe we can take all the infinite sequences of over R, that's also an infinite linear space. Then coming to the function spaces on functions, CAB, that is the vector space of all continuous real valued functions on interval, closed interval AB. If I am taking open interval AB also, it is possible. C over R is a vector space of all continuous real valued functions on the on R, on the real line itself. Now R of x is the set of all polynomials in X, and it has a basis x power n for every n element of script n. Now we were mentioning S star, C naught, C, L infinity and S and all, so we can relate those linear spaces. Something is contained in another like this. So S star is contained in C naught, which is again contained in C, and C is contained in L infinity, and L infinity is subset of S. These all things we know from our previous knowledge in real analysis and all. Now we are coming to the definition of linear maps. So what is a linear map? A map A from E1 to E2 between two linear spaces E1 and E2 is called linear if and only if for every x, y in E1 and for any two scalars a, b, we have a of ax plus by equal to a of ax plus b of ay. This already we know from our linear algebra paper, the linearity condition. Now some things or some particular things that we have to taken into account. If I am defining a linear map from E1 to E2, both E1 and E2 should be linear spaces over the same field of numbers. Then only I can define a function or a map, linear map from E1 to E2. Then about notation, we usually write AX instead of A of X. Then a linear map is also called a linear transformation, that is very obvious. Then about null spaces and range. A null space of A, or we will say kernel of A, denoted by kernel A is equal to set of all X element of E1 such that AX is equal to 0. So the null space is the set of all elements of the domain which are mapping to the identity of addition in E2. Now about the range of A or image of A, that is the collection of all AX, X element of E1. That means all the images of X in the domain. So moving on to isomorphisms. A map A from E1 to E2 between two linear spaces E1 and E2 is called an isomorphism if kernel A is equal to 0 and image A is equal to E2. And kernel A is equal to set 0, actually it is. So that is, we already know that isomorphism, then if it is 1 1 and on 2, 1 1 means the null space will have only 0, on 2 means the range will be equal to the codomain. So two linear spaces are isomorphic if there exists a 1 1 on 2 map between them. If kernel A is equal to 0, then the map is 1 1 or injective. If image A is E2, the map is on 2 or surjective. If the map is a bijection, that is both injective and surjective, then that map is called an invertible map. If A is a linear map which is invertible, then obviously A inverse will exist. Now we will define a linearly dependent set. A set of vectors x1, x2, etc. xn is called a linearly dependent set, and vectors, linearly dependent vectors, if there exist numbers or scalars a1, a2, etc. an, not all of them 0, so that the linear combination a1 x1 plus a2 x2 plus etc. plus an xn equal to 0. So here the linear combination of n vectors along with the multiplied with the scalars is 0, but sum of ai's will be non-zero. Then the set itself is linearly dependent. Then obviously if all the ai's are 0, then it will be linearly independent. That is what we are going to define. Linearly independent set. A set of vectors, n vectors, x1, x2, etc. xn is called a linearly independent set, and the vectors called linearly independent vectors if we have the linear combination a1 x1 plus a2 x2 plus etc. plus an xn equal to 0, then each ai is equal to 0 for every I is equal to 1, 2, etc. n. Now infinitely many vectors, if we have infinitely many vectors that are linearly independent, then we have an infinite linear space. That means infinitely many vectors x1, x2, etc. are linearly independent if for each k x1, x2, etc. xk are linearly independent. So as the k varies, still it will be linearly independent. Now something about linear combinations and span of a space. A vector beta in V is said to be a linear combination of the vectors alpha 1, alpha 2, etc. alpha n in V, provided there exist scalars c1, c2, etc. cn in the field F such that beta is summation I equal to 1 to n ci alpha I. This we have from the linear algebra basics. Then the linear span of a subset M of a linear space E is the intersection of all the subspaces of E containing M. We can also define span M as the set of all finite linear combinations of the vectors from M. Thus we have span M is equal to intersection over alpha, set of all E alpha such that E alpha contained in E and M contained in E alpha. So with that I am stopping. Okay, before that I will just define cosets of a linear space. So that I will explain in next class. We will just define it here. The collection of subsets X such that X is equal to X plus E1, X element of E, is called the set of collection of cosets of E. The sets with the square brackets X is called cosets of E. Then if you have two cosets X and Y, either they coincide or they are disjoint. Now this is an theorem given in the textbook. All things are basics already we have from the first semester, but still theorem 1.1.2. Let xi is equal xi I is equal to 1 to n be a maximal set of linearly independent vectors in E. That means maximal set means there is no linear independent extension of this set possible. So if I am taking a superset of this set, it will be linearly independent. So we are taking such a maximal set of linearly independent vectors in E. Then the number n is invariant and it is called the dimension of the space E. The vectors xi's, n vectors, forms a basis of E and we write dim E is equal to n. Any element, x element of E, can be represented uniquely as a linear combination of the basic vectors for some suitable scalars. These all things we know because if we have n vectors in the basis, any vector of the space can be written as linear combination of vectors of the basis. So with that I am concluding this video. Thank you.